reading of accelerometer data provides new insights for sleep and its association with mortality. So, for those who are not familiar with this word, mortality is the 사망률 그런 거랑 관련. So let's start with reading this abstract. Battery too light. So, are you done with reading this abstract? First of all, it looks too lengthy, and I think it contains so much redundant information. But I think the gap sentence is quite clear. The sentence beginning with this existing. So existing non-polysomnography sleep classification techniques mainly rely on heuristic method developed in relatively small cohort. So this is the key gap sentence. So I think their main contribution is they developed the algorithm and validated it with large data set. And maybe the other analysis is quite common things. They just calculate measure the sleep and association between other parameters. So is there any other comments here? Then let's start the main things here. So as the abstract said, the sleep is quite essential, but it's also quite complicated. So actually, many researchers still don't know many things about sleep. But at least we know that sleep is has some very complex structure. So I think most of you already have heard of REM sleep or non-REM sleep. So like this, the sleep stage, there are several sleep stages. For example, there's a non-REM sleep stage 1. This is the very next step of the wake state. So it goes this REM stage here, then it goes, as this number increases, it means that more deeper sleep. And then suddenly the sleep goes to REM sleep. So during this period, it's more like the brain is more active and people act more like some wake state, but not wake. And during this period, so people dream. So like this, and there are several sleep stages, and so this is kind of time series of sleep, and how the stages changes as time goes. First, we were in this wake state, and then it goes to this N1 stage, and go deep, and have deep sleep, and then suddenly come back to some REM sleep. And then again deep sleep, REM sleep. So you can see this kind of some kind of cycle. So this is kind of a regular structure of sleep. Then you may ask this thing, how these stages are measured? The golden standard of measuring this sleep stage is called the polysomnography. So I think most of you have heard of this thing, and the key part of determining the sleep stage is analyzing the brainwave, something called EEG. And when we, so using EEG, when we measure the brainwave, you can see some feature, the distinctive features of this time series for each stages. And so they just observe these patterns, and based on this pattern, they just classify its sleep stages. That's how this polysomnography, so sleep stage measurement using polysomnography works. But as you can see, this you need various some machines here, and you need to stay in some laboratory to get the polysomnography. So this is high cost, and there's also some technical complexity. So it's really hard to obtain some longitudinal data of the sleep stages for each people. So people have thought about many alternatives, and the more promising alternative is the actigraphy. So this actigraphy measures, so it's kind of watch, and it measures the acceleration made by this arm movement. So there are three directional, X, Y, Z directional acceleration is measured with this machine, and you can see this kind of time series data. This is time series of acceleration. And then based on this data, maybe we can make some machine learning or other statistical algorithm to classify each epoch into some sleep stages. So maybe 30-second epoch. And this is classified wake, non-REM, REM sleep. This was how previous method did to predict the sleep stages based on this actigraphy. But this author says that this process was quite not so perfect, because previous algorithms were validated only in small population, and also it relies on some handcrafted spatial temporal pictures. So what does it mean? So let me explain the details how the previous algorithm did. So we have this acceleration data.
Is it really used by Kondo?
Yeah.
Other method or Kondo?
Other method.
Oh.
So we divide each time series into, for example, 30-second epoch. And for each epoch, so for each 30-second window, we have the time series data, right? And using this time series data, we extract various features. For example, mean value of this time series or standard deviation, range. So we also can apply the Fourier transform and find what is the dominant frequency. So we collect this kind of several features and then use these features as an input of some machine learning algorithm. Then we train this machine learning or model, then we eventually classify these sleep stages. This is the regular thing how previous method used. But this author says that these features are really so subjective. So maybe we subjectively choose which feature we are going to use. So they wanted some more objective or more systemic way to extract those features. So this is the key idea of this study. So to do that, these authors developed some method called self-supervised learning. So, for example, we have this which one triaxial accelerometer data, time series data. Then we apply some transformation to this data, which is the reverse, permute, and time warp. For example, let's say that this is the original accelerometer data, time series data. The reverse is just swap, the flipped vector. Simply flip. And the permute is that randomly permute the order of this data. And time warp is that is choose some time point and it strengthens it or lengthens it or shortens it. So for example, originally there were 2 ones, but it shrink to 1. 2, 2, but it becomes 3, 2, and shrink 1, 3, 4, 1, and so it lengthens this 5. In this way, they apply this transformation.
In the time warp step, is the order by the permutation conserved, or is it?
Oh yeah, order is just conserved. It yeah.
You just increase the number of
yeah,
1 or reduce.
Yeah, right. Okay. Squeeze word number. So there are 3 types of. So they apply 3 types of transformation here, and then what they did is they trained a machine learning model, which classifies what this transformed data is. What is the type of this transformation? So, for example, if one plug in this time series, they just detect it or classify it whether it is the reverse transform data or permutation transform data or time warp transform data. What? So that's the idea. So by training this model, they thought that we can automatically train this feature extractor. So they thought that by training this model, so this model in some sense they eventually make some low dimensional vector here. So kind of embedded.
I see.
So and they think that this is the feature vector.
I see. So anyway, they will develop the neural network to distinguish the sleep stage, right?
Yeah.
But what you mean is, to develop that model,
Yeah.
we don't know which feature or which low dimensions are critical.
Right.
So that what they do is, before they label provide the sleep stage data, they just using the original data and then change it to the reverse,
Yeah.
permute, and time warp, and then we try to find the dimension which can distinguish these 3
Yeah.
features.
Yes.
They think that that's our universal.
They checked various times. Actually, there is a previous study. They checked various transformation, and they thought that this 3 transformation is the best. But
For the time series data.
it's kind of. I think I also agree that this is kind of heuristic, right?
Yeah, heuristic, but anyway, let's think about it. Anyway, it will work well, I guess.
Yeah, it is something. Yeah.
Everyone, let's think about it. Why? Kind of our job is, for given time series data, for certain part, we'll say sleep stage at 1, certain part sleep stage 2. We will give a label for them.
Yeah.
We'll perform the supervised learning. Before it, we try to find the key feature in this way. Basically, we do some sort of supervised PCA
Right, exactly.
But that supervised is very clever. We don't need any label for given data. We reverse it, permute it, and time work.
Maybe a similar thing would be just the autoencoder. Autoencoder is just how to replicate the original, but this is totally different.
Yeah, exactly. That's why.
That's the key idea, but yeah,
Why this is useful? Let's think about. I think this is the most important thing in this paper, I guess.
Right.
Let's think about it. We want to develop some machine. And then, if the machine can distinguish these three transformation, why this machine could be universally working well? Of course, we need to provide label data later, but why distinguishing this picture is a fundamental thing to do. I think this is a cool idea, I think, because kind of exactly what currently you are doing is from the time series data, you extract a feature for a certain feature, and then you're trying to use it to distinguish the disease and non-disease, right? But that feature is determined by someone, right?
Yeah.
But here, they don't use some predetermined feature. How they select the feature is plug in the certain time series data. It could be SpO2 or heart rate or whatever. Which feature allowed to distinguish the normal and reverse, random permute, and time. They think that these are really important features. If you want to use this data to do something, to make a prediction. It's not intuitive. Let's think about it. I think this is the most important moment of this paper. Isn't it? If it worked well, isn't it cool? For the supervised learning, we will do the supervised learning, right? Typically for the supervised learning, how we select the feature? We select the train and test data set, we select some feature which perform well for the train and then use it. But for that kind of, we need a lot of data. But here, before doing it, let's select the feature. How to do it? Which can distinguish original, reverse, permute, time. Why certain feature which can distinguish this transformation? Why could be the backbone for anything? For some time, I really admire engineer.
They don't need to explain.
They don't need to explain, but anyway, how they find this? Seriously. And how they come up with this kind of idea? I guess someone did a try. 진짜 신기하다. 이걸로만 피처 로우 디멘전 한 다음에 쭉 갈 거야? 여기는 더
네.
뭐 안 하고?
정확하게는 so in the next step they just embed this network here and get feature, then they apply some LST and some more further structure here, and then they eventually get
But
this.
anyway, dimension reduction is
Yeah.
done via this way. Anyway, basically PCA is done. But how the PC1, PC2, PC3, PC4 are selected is how to distinguish the original one and reverse permute.
It looks like a feature selection,
Mhm.
so they want to discriminate, they want to distinguish the original. If data have some temporal structure,
Mm.
specific temporal structure, then temporal structure should be should have a very specific infrastructure. So it should be separate from the permuted one or reverse one.
Yeah. So basically, what they tell us is, let's say we want to use time series data shape to tell something, your OSA or not, or your stage 1 or stage 2, stage 3. Anyway, we want to use shape of the data to tell something. For that purpose, the feature which can distinguish original reverse, original permutation, original time warp, that feature basically they said is critical to use the shape of the time series data. That's what they are telling, I think. If I do the overstatement, if you want to use the shape of time series data to do something, you have to select a feature which can distinguish original and reverse. Why distinguish the original reverse and original permutation are critical to use the shape?
Well, actually, in this classification model, no original.
Oh, just
Just this.
there's no original.
No original.
네? 더 신기하네. Why?
So
Even there is no original. Hopefully there is original.
yeah.
오리지널 데이터가 주어져서. 인풋이 오리지널 데이터인가? 아닌데.
인풋은
그
트랜스폼 된 게 들어가고
맞지?
된 게 세 개 중에 하나로 이제 하고 있는.
어우씨.
이게 저도 이게 왜 됐는지 잘 모르겠어요.
야, 근데 even there is no original. 더 헷갈린다. Only reverse, only permutation, only time one. Undergraduate student, you have most fresh brain. Any idea? 왜 될까? 원래 거랑 원래부터 그렇지. 이게 여기다. 이게 퍼미트 된 거야.
여기인지 퍼미트인지를 구분하는 게 중요하다는 거죠.
근데 굳이 역을 왜 하냐? 그냥 오리지널이랑 차라리 퍼미트를 구분한 거고.
세 개가 세트로 들어가는 건 아니지.
세트로요?
그건 아니지.
셋 중에 하나만 무조건 들어가.
그렇지. 내 머리는 이해가 안 된다. Any smarter person can any intuition? Yeah, because if we can understand why this worked well, then it's so powerful. Is there anyone who handled the time series data in this room? Hands up. I'm handling the time series data. Hands up. You. ActiveWatch is time series data. You have a time or not x-axis? Yeah, hands up. See? All of your life can be affected by this thing. 진짜 모르겠는데. Is there anyone who can ask to ChatGPT why reverse permutation and blah blah thing can be helpful?
이세 분류하면 된다라고 생각하고 이세 가지 트랜스포메이션 종류를 골라내시는 걸 안 해요.
안 하겠지. 이유 설명 안 했지 얘들.
기존 연구에서
그렇게 했다.
이것저것 더 해본 거가 있을 텐데.
그러니까 기존 연구에서 이걸 했더니 잘 되더라 하겠지.
네. 그럼
사실 엔지니어들은 왜 잘 되는지까지는 보통 가지. 과학의 영역에 들어온 것이지. 그래서 약간 근대 논문들 보면 보통 그냥 왜 그런지 모르고 했는데 잘 됐어. 그게 논문이란다. 5% 증가. 그래서 언제 잘 되고 언제 못 되고 이런 거는 잘 몰라. 안타깝게도. 그러니까 distinguish reverse permutation timer. Wow. Anyway, this method looks like very popular. It has been used for speech recognition, financial forecasting, medical diagnosis already in a time-dependent manner. It looks like work well. They said this feature forced the model to pay closer attention to temporal structures. Wow. It was very famous example is in human activity recognition model development, distinguishing between walking forward and backward improved the understanding of the motion pattern.
I think that's the very previous study of this, with the same same author. It is also published in MPJ Digital Medicine.
I see. And it's the one example. Why using the permutation? Kind of, if they can distinguish the permutation, then that means they can detect the abnormal time series data.
Yeah, right.
From the given real time series. If our picture can be used to tell this is permuted or not, that means permuted means basically data is something wrong. Then for the real world data, definitely there is some part should be some error or whatever, very weird thing. Then this permutation feature can tell that this part is unbelievable. I think this is one useful thing we can get. But anyway, although we cannot fully understand it, it's cool if it worked well. Very, very cool idea and non-intuitive. It's something we can think during the weekend. Please think about it. Because if we think this, then we can improve the management. Okay, let me move on. Sorry. Yes. Anyway, they do very interesting approach which we cannot understand. Anyway, they select a feature.
Yeah, right. They select feature and they plug in to another some machine neural network model, STM, and then they eventually get this prediction. So actually, I prepared. I was also interested in what is the LSTM, so I prepared to explain what is the LSTM. So let's see. I just briefly prepared this. So to understand the LSTM, we need to understand recurrent neural network first. Recurrent neural network the idea is simple. So we will plug in some time series data as a sequential input, and the previous output is used as an input of a next prediction. That's so. So for example, let's say that we have this sequential data here. We will plug in step by step, and let's simply say that this neural network just calculate this equation. Then we plug in 1 here. So this is first step. So maybe we can, let's say that for H0 is just 0. Then the output would be 2, right? For this equation. Then we plug in x1 value here. And because the previous output was 2, if we plug in here, we get 4. And then we plug in 2 here. 2 plus 4 plus 1 is 7. This is how the RNN works. That's all. But LSTM is a little bit more complicated. So it uses not only this previous output HT, but also uses this CT. We will call this a cell state. So it's kind of the main memory of this neural network. The output would be mainly determined by cell state, and the cell state is keep updated depending on previous output and current input. So specifically, this CT cell state is updated with these 2 processes, F and I. F is represent the forget, and I represent input. So let's see forget first. So FT value here is determined by current input and previous output, and it plug into with some basic neural network structure, and then we apply 2 sigmoid function. Sigmoid function is this. That means this value would be between 0 and 1. If value is 1, we will keep this previous state. But if it is 0, that means we will completely forget the previous state. So we will determine our state mainly based on just current. That's what this forget gate means. And then the input gate determines which value we want to update based on this input and output. So this T2 dot is the value to update, and IT just determines the kind of weight to this current update value. So these 2 values are determined based on this current input and previous output. And then again, so if IT is equal to 1, then we will fully update with this value to update. And then if IT is 0, then we just ignore this current input. And based on these 2 gates, the current state, the cell state is updated, and with this updated CT, it passes through some activation function and it determines output. But also this output is filtered by current input and output. So the output is mainly determined by cell state, but it is also filtered by input and output with the value of this OT. Yeah, that's all. That's the basic, the structure of LSTM. So maybe there could be some modification and other version of this LSTM, but people say that this is the basic of this LSTM, and yeah, let's move on. So anyway, they uses this previously trained self-supervised learning model, and then LSTM, they eventually predict this polynomial, these 6 stages. Then the key question we need to ask is how accurately this model called SlimNet can predict these 6 stages. So to evaluate that, we need some parameters. We need to quantify its accuracy or its performance, right? So to do that, we usually use this confusion matrix. So yeah, actually there are more stages, but let's just think about the problem. We just classify sleep and wake. So for each time point, it is either wake or sleep. The actual value would be either wake or sleep. And for each that time point, we can predict either wake or sleep. So, and this number represents among the total the data points we need to predict how many data points was actually awake and we predicted it as wake. This is and the other components are determined the same manner. So this is called the confusion matrix, and yeah, this is the basic step to evaluate this kind of classification model. So this cell usually we classify it true or false, or positive and negative. So let's say that the wake is positive, sleep is negative. So this is actually the positive, and we actually predict this as a wake. So we call this true positive. In other words, so we predicted it as a wake, but it was originally sleep. So we firstly predicted as a positive. So that's why we call this false positive. In the same manner, so false negative and true negative is determined. And based on these values, we can calculate this kind of values called precision, recall or sensitivity, specificity, accuracy. So accuracy is, I think most of you are familiar with accuracy, but in this case, accuracy is not so preferable because, for example, if the data is imbalanced, so let's draw like this. So this is actual, this is predicted, wake, sleep, wake, sleep. So actual sleep is, for example, we predicted as a whole thing as a sleep, but in real only 1 and 99. This is 2, 0. So 90, 10. So let's assume this kind of situation. So what would be the accuracy here?
So 0.9.
Yeah, 90%. But can you really think that this is 90% accurate? We just predict it as a whole thing is asleep. So we cannot say that this performs well, right? So in this sense, accuracy is not a good metric to evaluate performance. So that's why we need to consider other precision. Precision means that so among the whole proportion that we predicted as a wake, how much of them is truly wake? Something like that. And this sensitivity means that among the actual wake, what proportion we predicted as, we correctly predicted. So in this sense, yeah, we can use these parameters. And so that means we need to consider some pairs of values. But this is, we don't like it. So to use only a single value, we sometimes use this F1 value. This is the harmonic mean between precision and recall. That means this is, so harmonic mean is a little bit weighted to some lower values. So that's why, so that means to maximize this F1 value, we need to increase both precision and recall. So that means we actually matches this line, and also it actually matches this line. So if F1 value is high, then we may say that this model performs very good. Then you might have this kind of question: what if we have more than 2 classes? I'm not sure whether this is really accepted one, but some studies use this kind of thing. So, for example, let's say we have 3 classes confusion matrix. Then we can collapse it into two class the confusion matrix. For example, we have actual slip and not slip. We can classify it as wake and not wake. Then the amount of the actual wake and we predict it as wake is still 10, and the amount of actually not wake but we predict it as wake is this portion, right? That is why I write 2 here. And these 4 cells are classified into not wake and we predict as not wake. So in this way we can make this kind of 3 collapsed confusion matrix. And for each confusion matrices, we can calculate the F1 value. Then the mean value of this F1 value can be used in some sense as a metric to evaluate this classifier. Maybe someone said that we can give some weight as a data they use, but so famous Python package, when we use the F1 value for this multi-class classifier, they calculate F1 value in this way. Maybe we can use this metric if you want to train the multi-class classifier.
But if we have this multi 3x3 matrix, confusion matrix, can we define the TPTM, FPF, and
So this is TP is determined only binary because we need to set what is positive and what is negative. So that's why we collapse them into 2 classes.
yeah, but for instance, if we predict the wake, then TP should be actually it's wake, then we can call TP, right?
Yeah, right.
But if rem and non-rem, we can call negative, false.
Yeah, this is this confusion matrix.
Okay, can we merge? Okay. Yes. Okay. We need 2 by 2.
Yeah. And actually, there is another metric we can use, which is I think some of those folks heard of Cohen kappa. So the interpretation is quite tricky. Let me try my best to explain this. So let's assume this very bad case. So we predict it as whole thing is slip, but actually slip is 99 and wake is 1. So the accuracy is 0.99. And here, but there's a possibility that we just occasionally correct the answer. So let's assume that we make a prediction randomly while maintaining the prediction ratio. So we just randomly predict wake, but we maintain the ratio. So that means we don't predict any wake, but we will say the slip. Then we give a random prediction. Then the probability that we can occasionally correct the answer would be the 0, because we will not give any prediction. But for slip, it will be so this probably will be 1, and the probability of being hit is 0.99. So this prediction is 0.99. And if we sum up them, we can calculate this PE, which represents probability of occasionally making a correct answer. Then what coherence part means is that we will subtract this occasionally happened accurate answers. So it is determined by this equation. So we will subtract this to just ignore the occasionally corrected cases, and we just normalize it to make the maximum value as 1. That's the meaning of coherence kappa.
Like it.
Yeah. So the good thing is that this can be used even for these multi-class cases. So for example, if we have this kind of confusion matrix, we can calculate the accuracy, and also we can calculate the probability that occasionally can make a correct answer in this way. And then we sum them and calculate this PE, and if we calculate the kappa value here, this value is quite large because we have made a really good predictions. And so people say that if this value is very high, this is almost perfect. And if this value is between 0.41, 0.6, then it has a moderate performance. Yeah. So in this, using this one, we can also evaluate the performance of the classifier, and I've seen so many papers using these values as a metric.
Because they give us some meaning. For instance, 0.5.
Yeah.
That means it's half of the maximal possible accuracy rate. 1 minus PE, the denominator is compared to the random thing, how much we can make an improvement. That is 1 minus PE.
Yeah, that's right.
And then point kappa become 0.5 means kappa is half of that.
Yeah, right.
So compared to the maximum improvement, we can achieve the half of
Yeah.
that is point kappa value 0.5. It's pretty good quantity because they give a image.
Yeah, right.
I like it. Yes.
So using this matrix, so they applied it to, so they first applied the random for it with handcrafted some features, and then they use SlimNet, and the last one is the SlimNet with self-supervised learning. So that means the second one is use the same structure, but they also train the original ResNet part. But so they said that okay, so SlimNet with self-supervised learning gives the highest accuracy and highest F1 value, something like that. But I think it's not so perfect. Still, we need to improve more to we need to improve more. And also this is something called Bland-Altman plot. So this represents the difference between so we first classify all sleep and wake cases, and then we calculate the total sleep time during some period. And there would be some true total sleep time and predicted total sleep time, right? Then we plot it for the real total sleep time value. We plotted the differences between the error. And they said that so the bias of this error is almost minimum, but I think still the error is quite large.
Yes.
But anyway, they said that they achieved some moderate accuracy. So because this is multi-class classification, I think maybe people think that this is okay. This is in some sense good performance. But I think we can still improve. Yeah, so far I introduced their new new model structure and its performance. And then the last thing would be the application of this method to very large data set. So I think the previous journal club already had introduced some papers using this UK Biobank data, and they also use this. And the good thing is that it's really large data. So for this many people, for each people we can collect this 7-layer active everywhere data, and by applying this prediction, we can get the sleep information. So how long did they slept, what is the length of the REM, something like that. And then also, they also collected some self-report survey or baseline assessment. And then, so by some processes, they get some demographics and also information about the mortality. Then they analyze the relationship between sleep duration or sleep efficiency and the mortality. So they analyze this amount of period of this whole people, and during the whole tracking, they observed only 1,600 dies. And so with this data, maybe we can plot the survivor function, which represent how many portion of people can alive at this time point. Maybe this is maybe you can think that with different scale of the age. So how many people is still alive with this age? We can plot the survival function, and then so you can think that this t, random variable t, is the stopping point of for death. Then with this random variable, we can also consider this hazard function. This represents some instantaneous failure or death rate, which is, so with this, the condition on is these people is still alive at time t. What would be the probability that really short time period? What is the instantaneous death rate? This is what we call hazard function. And if we calculate this, we can easily derive that this is just nothing but this derivative of this survival function divided by this survival function.
So if you think that S prime of S, what is the derivative of this? Think about it. When we get the S prime over S, you learn at high school. It's a derivative of what?
No.
Derivative of log S, right?
Yeah. So
Oh yeah,
this is the example.
okay,
Yeah.
okay.
If the survival function is this exponential function, then if we calculate this hazard function would be just 1. That means the death rate is just constant. Then in that case, it gives this exponential decay.
But it's a derivative of log, that means it's basically a derivative of exponent. Does it make sense? If it's a e to the t squared minus t squared, it will be minus 2t.
Yeah.
Okay.
Yeah. So and then for example, so depending on whether this person or searching group who slept less than 6. So actually this graph is I just borrowed in
Other paper.
So maybe we can divide them into 2 groups who slept less than 6 hours or larger than 6 hours. Then maybe some decay rate could be different. So that means for each group, the hazard function would be different, and they apply some Cox proportional hazard regression. That means they just predict the ratio between this hazard function, and they assume that this is time independent, but only determined by some variable. And here, for example, this x means that x has 1 value if these people are in this group, and 0 in this way. Then so by applying some regression, maybe we can estimate this parameter beta. What if the beta is minus ln2? That means the ratio would be 1/2. That means for those sleep duration is larger than 6 hours, there some instantaneous death rate would be half of compared to those who slept less than 6 hours. So in this way, we can analyze the association between such sleep and death rate. And this is the real result. So here, the baseline is just sleep between 6 and 7.9. But here, you can see that this hazard ratio, which is the ratio between these two values, is slightly larger for those who slept less than 6 hours. And this does not irrelevant to sleep efficiency. So maybe the key point is that you need to sleep longer than 6 hours. And yeah, that's the end of the content. So in summary, so we have seen the key idea, which is using self-supervised learning as a feature extractor. And also we learned some basic concepts of LSTM. And here we learned how to evaluate this multi-class classification model. And also we can at least we know how to analyze the association between some factors and this kind of death rate or survival rate. Yeah, thanks for listening.
Yeah, any questions?
So in the first quarter, they set the baseline as 6 hours. So how can we determine this baseline sleep time?
Baseline sleep time is so they did divide into 6.
Yes.
So they didn't explain why they set as a 6 as a threshold, but I heard many people say that you need to sleep at least 6 hours. I think they are affected that kind of previous step or previous work.
Yeah, please. Yeah. Any other questions?
When they apply the time transformation, did they randomly sample the source data?
Randomly sample.
Yeah, so.
Yeah. The time series was originally come from real data. Yeah, here real triaxial data, and they randomly. I think they randomly sample.
Randomly sample and then randomly apply these 3
Yeah.
transformations.
And here also there so the permit is of course the random, and also this time work. So choosing the time point to squeeze and stretch is also random.
They open the code or no?
Oh, I think they opened the code.
They open.
Yeah. Also, some of the passage and acceleration data is also available.
The UK. Oh, yeah.
I think not UK.
But their own data are open.
Yeah. Maybe we can use some.
So they open the PSG and ActiveWatch.
Yeah.
Actigraphy.
Yeah. So our main data was just activity count, but their data is more finely sampled accelerometer data.
Do you think code is available now? Is there anyone who can use this code for your project?
So when I
It doesn't
first
need to be this purpose.
when I first saw that, so maybe don't use project about predicting the tau C based on
Jian? Jian is not here. Yeah, Dongju, maybe. 타우시 예측하는 거. 시계열 데이터. 시계열 데이터가 있고 라벨이 다 있는 거지.
That's basically classification. Not
a regression.
But we can do.
Yeah, so this classification is only used for feature extraction.
So that's why I think we can do it.
We can
The classification.
we can randomly revise this part and use it as some regression. So I also think that studying about the underlying mechanism or underlying finding out the underlying reason why this works would be also very important.
classification. 숫자로 리그레이션을 하죠. 숫자. 왜 보면 좋은 거죠? 그렇죠? 시계열 데이터가 보고 이렇게 한번 해본다. 얘는 안 되면 나가지고 인생에 쓰면 괜찮아. 공주야? 야, 여기 안 해볼래?
but
이거 걱정되는 파트 있구나.
people pay a bit. They have 16,000 people.
Data of whole people? No. Only sorry. How many? They only opens only some parts of it. So they have various data set to validate.
그러면 이 논문에서는 거의 6만 명 사용.
네.
테스트.
그러니까 요 기존 프로세스는 스텝이 세 가지가 있는 거잖아요. 처음에 언슈퍼바이저드 할 때는 10만 명이 잡혔어요. 언슈퍼바이저. 셀프 슈퍼바이저 러닝 할 때는 10만 명을 썼고 거기에서 이 학습대비 모듈을 그냥 갖고 와서 그 다음에 슬립 스테이지를 테스트할 때는 그러니까 체이징할 때는 1000개 데이터. 1000명 데이터. 1000명 데이터.
저희도 그냥 그대로 갖다 써도
네, 갖다 써도 되긴 할 텐데
근데 왠지 갖다 써도 되지 않나? 밑으로 나와야죠.
네?
왜 가져?
저희 100명
데이터를 알아서 만들어가지고
안될 수.
그냥 그거
어차피 커런트랑 액티비티 아니 우리 액티비티 데이터는 100명이 아니라 수백 명 개이지. 아주 뗄거 100명. 그다음
저희가 가지고 있는
모든 것들 어차피 액티비티 리버스랑 퍼뮤트랑 타임워크 이걸 해서 그걸 디텍트하는 거니까 그러니까 우리가 갖고 있는 뭐 무드 디소더 포함해서 모든 타임 시리즈 데이터 다 때려 넣어야지.
그러면 학습은 될 텐데, 그러니까 그러면 저희 거만에 그게 만들어지는 게 뭐냐면 얘들은 액셀러레이션이지 액티비티 카운트가 안 될 거예요.
그러니까 우리 카운트로
해야 될 거면
카운트로 피처 익스트랙션까지만 하고 그 다음에 그 익스트랙된 피처를 가지고 그렇죠?
네, 저희는 거기서 아마 모델 구조를 조금 바꿔줄 수 있는 게 여기 피처 벡터가 크게 너무 커요. 1000개는 1000 넘거든요. 이거 좀 줄여낼 수 있을 것 같아요. 다행히 코드를 오픈으로 해놔가지고 바꾸는 건 그렇게 어렵지 않을 것 같아요.
되게 나이브한 질문이에요.
네.
이렇게 그 피처를 고른 다음에 오리지널 스트럭처 공부도 할 수 있고
그게 오토 인코더. 네,
저렇게
그러니까
해서 저 세 가지 이걸로 골라진 애들이 쉐입이
아,
잘 모르지만
그러니까
그러니까 뭐
그거는 좀 다른 아예 다른 문제로 가는데 오토 인코더가 뭐냐면 얘는 이렇게 해서 이렇게 문제로 이렇게 바꿔버렸잖아요. 얘를 심플로 하나 더 바꿔놔가지고 원래 거를 복구하도록 만드는 게 오토 인코더잖아요. 코드 여기서 하는 거왜 오토 인코더를 안 쓰고 이걸 썼을까?
그거에다가 얘 코드를 줘가지고
그렇죠.
저거만 뽑아서 그걸로 합식해서 인스트럭션을 보면
네.
우리가 템포럴 스트럭처에서 어떤 피처를 뽑아서 보는지 데이터를 비교될 거예요.
아,
그러니까 어떤 게 복구되는지
그러게요. 네, 그거 흥미로 재밌는 연구 방향일 것 같아요. 그러니까 왜 이게 잘 됐는지를 연구하는, 잘 됐는지를 연구하기 위해서 단순히 오토 인코더를 써서 학습돼서 복구되는 애들이랑 얘를 써서 얘를
거기서 복구돼요.
여기서 이거 거꾸로 다시 복구하는 애들은 무슨 차이가 있을까?
웹만 썼는데
저는 그거를 연구하는 것도 꽤 재밌는 연구 주제일 것 같아요.
된다 그래서 할 수 있을 것 같아요. 피처를 할 수 있을 것 같아요. 사실 그런 피처를 바꿔서 해줄 수도 네. Anyway, I like it. This maybe yeah. SPO2 hard someday. Currently, you're using the manual feature. But why not?
There was one paper like Geiger. They tried to use CNN to use some abstract feature. But maybe they didn't use this.
Yeah, exactly. But this is more specific for time series data. That's why I like it. Maybe you may also want to study this paper. In this paper, they cite the original paper where they tested this various transformation data. You may want to read it. I think I like it. Because always manual feature means standard deviation, blah blah blah. We are always unsuspicious. We are always suspicious whether that is sufficient or we are in the correct way. But this is more objective. 더 엘레강트하게 똑같이 잘 되더라도 약간 매뉴얼은 그냥 주먹 공식으로 보니까 초식대로. Any other people who think you can use this idea?
How many data they use?
1,000.
So for self-supervised learning, they use more than 100,000
Oh,
Feature
people
extraction.
for feature restriction.
100,000 people? 100,000? Because they use the UK Biobank.
Yeah, right.
Yeah. I see.
But for sleep stage prediction, they only use 1,000 people.
Okay. So feature extraction, they use the PSG data of the 100,000. No. Yeah, active.
Yeah,
Accelerometer data
Yeah.
for 100,000 people.
yeah, right.
then how long the time series data?
7 days.
7 days.
7 days, and they split it into 30 seconds apple.
3 seconds, 7 days. Wow, so long.
Hey guys, I think let's search this first. Activity count data, reverse, permute, time warp. It's possible someone already did it. Then we can just bring that pictures. Maybe for you guys, SPO2. part with that key. Let's search it. If there's someone did it, we can just use it. That's another way we can pursue. Yeah, although we don't understand why it worked, but it looks very elegant in this. Any other question? Okay, and then let's thank Yumin. Okay.
혹시 사진 찍어야 되나? 아 맞다. 네.
녹화는 끄시고